In this unit, we're going to be looking at some different test statistics to calculate and find their probabilities and use those to make decisions about the claimed value for the population. I want to stress that we already know this. We've used the equation for z for the means before. We're just going to add another equation here for proportions, and then there's another one for means called a t distribution instead of z, which just adjusts the value because you only know the sample standard deviation and not the population standard deviation. But it's the same idea. And we know how to calculate these, and we know how to find the areas in a calculator with the normal CDF function. So we're still going to be using normal distributions, the normal CDF function in the calculator. We're also going to be learning other methods of solving these problems with your calculator as we go. So again, we know this already. We're going to calculate a test statistic, which you know how to do. We're going to find its probability, which you know how to do. And now the only thing we're adding is that we're going to use that probability to determine if a sample is significantly different from the population or claimed value in the null hypothesis. So there's two tools that we're going to talk about. The first one is the critical region, and this is one that we've already been doing. We've been looking at probabilities of particular values. What we're going to do with the critical region way to solve these problems is set a certain probability for a problem and say if the probability that you calculate is any smaller than that set probability, then it's unlikely that the claimed value in the null hypothesis is true, so you would reject the null hypothesis. Okay, so I'll draw some pictures for you for this in a minute. But the critical region, the official definition is the set of all values of the test statistic that would cause you to reject the null hypothesis. And again, it's an area, so a shaded region in your distribution. And the predetermined level or probability, we're going to use the symbol alpha. So it's the Greek letter alpha. It's like a script A. And alpha is an area. And again, it has to be predetermined. You need to choose your value of alpha before you start a problem. And most of the problems that you do in this class, it will be given to you in the problem what value to use. So we're going to learn how to do these problems two ways. We're either going to calculate the test statistic and then find the area that associates with that and compare that area to alpha, which is the predetermined area, or you can just simply plug in a bunch of numbers into your calculator to get the area directly and then compare that to alpha. So let's look at a couple examples. We're going to look at one-tailed tests. A one-tailed test means that the alternative hypothesis either says less than, which would be left-tailed, and if the alternative hypothesis is greater than, we're going to do right-tailed. So I'll do one of each. This one will be left-tailed. So when we use the calculation for z, we get a test statistic and say it's some cutoff, and we'd look for the probability that it's over to the left. Okay. But what we're going to do in this critical region is set some predetermined value of an area, which is called alpha, and then we're going to compare it to the probability of your test statistic. So if the probability of your test statistic ends up just being this little part shaded in red, then your probability is lower. If your probability ended up being over here to include all of this, then your probability is greater than alpha. So that's what we're going to be doing with alpha. But again, alpha is predetermined. You choose it before you start the problem, and then you compare your calculated area to that. So a right-tailed, same idea, except we're going to be going to the right. So now we're going to choose some predetermined value of alpha, some probability. And then again, when you calculate your test statistic and the probability that goes along with that, you'll compare it in size to the alpha that you chose beforehand. So both of those areas are alpha. And this one is right-tailed test. A two-tailed test would be if your alternative hypothesis says not equal to. That means we need to look at both sides. And alpha has to be the area of both sides added together. Which means that whatever value you choose for alpha, half of it is over here on the left, so alpha over 2, and half of it is over here on the right, alpha over 2. So instead of all of alpha being on one tail, like it was in the one-tailed tests, half of alpha is on the left tail and half of alpha is on the right tail when you are doing a two-tailed test. So again, what you're going to be doing with this then is compare your calculated probability to the predetermined alpha probability to make decisions. And we'll learn some rules about making decisions. The alpha we were just talking about is also known as the significance level. So the alpha is the probability that the test statistic will fall in the critical region if the null hypothesis is true. It's also the probability of a type 1 error, which we'll talk about in a different video. So some common choices that they'll typically give you for alpha in a problem. Sometimes you may see 0.1, although that's kind of large for alpha. Probably the most common value for alpha would be 0.05, but it can also be smaller. And in something like clinical trials where you're doing something that's really important to get right, you want your type 1 error to be really small. So you might use something like less than 0.0001 or something like that as your value of alpha. And then again, if you're doing a two-tailed test, you need that to get split up into two of your tails. So if we just say that alpha is 0.05, if you're doing a one-tailed test, let's go to the left side, all of that is in one tail. So this is a left-tailed test. And if you're doing a two-tailed test, we have to look at both sides. So half of alpha is over here. And half of alpha is over here. So it gets split up into 0.025 in each tail. So always check to make sure you're doing, if you're doing a two-tailed test, that you've split your alpha into the two separate tails. And that way you'll be able to compare your probability accurately. Alright, the next type of way to solve these problems is called the critical value method. And the critical value, instead of looking at the probability for something, we're just going to be comparing z-scores, or, and when we get to it, t. So you'll be looking at a z that you've calculated, so the test statistic, and you're going to be looking at some predetermined z that's called a critical value, so we're going to call it z alpha. And this, again, this one's predetermined. Just like we would predetermine what alpha is before we start, we'd have to predetermine what the critical value of a test statistic is before we start. These two methods are related to each other, and you'll see when I draw the pictures that they're actually fairly similar. It's just that in the critical value method, we're not going to be looking for the probabilities. We're just going to be looking at the value of z. Alright, so the first one, we have a two-tailed alternative hypothesis. And alpha is 0.1. So, but two-tailed, we have to split that in half. So over here, half of 0.1 is 0.05 over here. And same thing over here. And if we were using the critical region method, that's all we would need to do. But since we're going to use the critical value method, we just want to know what is this value. And since it's a two-tailed test, I'm going to write z alpha over 2, because this is alpha over 2 over here, and this is alpha over 2 over here. They're symmetrical, so whatever value you get for the positive z, it would be the same number over here, except negative. So negative z alpha over 2. And then we can solve for either one, because we have an area. We can use our inverse normal function. And let's just do the negative one. So the negative one, the area to the left of that is 0.05. The z distribution has a mean of 0 and a standard deviation of 1. And we get the value negative 1.645 if you were to plug that into your calculator. So this negative z over here is negative 1.645. The positive z, the mirror image, would be positive 1.645. That's our critical value of z. So we can write z alpha over 2, since it's a two-tailed test, equals, I'm just going to use the positive number. That's typically what we would end up using to do this method, is the positive one. And then again, you would calculate your z for your sample, and that would be your test z, and you compare that to z alpha. All right, in a one-tailed test, this one is left-tailed. So we're going to be over just on the left side. We're given that alpha equals 0.1, and all of it's over here. We don't have to split it up. But then we want this number for z, so z alpha. And again, if we have an area, we can calculate z. So the area to the left is 0.1. Z has a mean of 0 and standard deviation of 1. And the z-score down on this axis, let's make it negative, is negative 1.28. That would be your critical value of z that you could use to compare to your test z to make a decision. Okay. The last thing on this page is about the p-value, and you have already calculated p-values. We just didn't call it that yet. So the probability that we've been calculating is p-value. And when you're doing problems, use the whole phrase p-value. Don't shorten it up to p, because you'll end up getting it confused with p for proportion. So always write out the phrase p-value when you're indicating what your p-value is. So anytime that we have ever calculated a probability from a test statistic, so say we were doing something like this, and we got this area, that is a p-value. Okay. So we've always been just calling it probability. Now we're adding a special term to it. But again, it's not a new concept, just a new name. Okay. And then in the next video, we're going to see how we're going to use the p-value. We're going to compare the p-value to alpha to draw conclusions. And again, just a quick reminder, always check your alternative hypothesis to know if you're looking for the left side, the right side, or both tails in a test to make sure that you're getting the right p-value.